Thursday and on Friday, and I'm hoping we're done with 9. Our next test will be a couple weeks. It'll be into February somewhat. It'll be on 8, 9, and 10. And you guys, we had a meeting, and Dr. Page made it out like you guys will be coming back. We had a meeting on Friday that you guys, the hybrid is definitely going to be happening at least for a few weeks, it sounds like, which is good news. Some ways almost like remote, because remote we can move faster, but I'd much rather hang out with you guys and instead of just seeing your faces on a Google Meet to actually be with you. So anyways, that is the plan. That is what's going on. So let me get started here. Any questions? Any questions you guys have? Ready to go? Okay. So here we go. So back where we left off, and okay, so I'm going to go back to what I've got here, what I had on the board. Okay, so this is where we were, and we were almost done with this page, is actually where we were. So again, you guys have to kind of talk to me about if you can see something or not see something. And we've been doing shapes. So again, I can't see the screen. And so Karen, Mason, or anybody, can you guys see over here?
Yeah, we can see over there.
The notes?
Mm-hmm.
Can you see the notes?
Yeah, we can see both the notes and the whiteboard.
Okay, good. So the last shape we're on, and I talked about this on Friday at the end of class, was XEF4. And XEF4, and again, make sure you guys can see this. And I think I did the dot structure, but let me just review this. Again, you guys could ask a really good question here. You could go, wait, xenon is a noble gas. And noble gases shouldn't react. And you're right. Noble gases usually don't react, but they do react a little bit. And so xenon, since it's in this compound, we're just going to go through the normal rules. So we're going to count the valence electrons. So xenon has 8 valence electrons. Fluorine has 7. 7 times 4 is 28. So we get 36 total dots. Okay, and then again, the element written first goes in the middle, and then the fluorines are going to go around it. So here's the dot structure. We've done a lot of dot structures now. And on that test that we'll take in a couple weeks on 8, 9, and 10, we'll definitely be, and we're going to do a kind of a lab activity that we'll do, maybe not next week, but the week after, where you'll actually build molecules, and you'll build and you'll show, try and diagram this in 3 dimensions the best you can. But okay, so now I fill the octets. And if I count, I got 8, 16, 24, 32, but I get 36. So again, off the central atom, I put the 2 dots. So remember our steps here, and there definitely are things that you're going to have to memorize. A lot of new shapes. You got to know the bond angles. But in terms of the processes, it's still the same thing. Do the dots, count the electron domain. So remember, a bond is an electron domain. So 1, 2, 3, 4. And then a pair is 5, 6. So there's 6 electron domains. So our final shape then, and it's the very bottom one on this slide. So the very bottom one you can see, it's going to be called square planar. Okay, so if I go back to the notes. Okay, so if I'm down here now, I'm on the very bottom one. So again, I did the dot structure. I have 6 electron domains, so A, B, 4, E2. So A is Xe, the B4 is the F4, and the E2 are the non-bonding pairs. And so the shape here, and this goes back as a derivative of the octahedral shape. So here was the octahedral shape, and the shape that we had just before this on Friday. So here was octahedral, okay, 6 electron domains, so that's the base shape. If we had one non-bonding pair, which we had an SbCl2 negative, SbCl5 negative 2, the non-bonding pair comes off here. And so what we have is in the horizontal, in the equatorial, we have a square, but then we have, it looks like a pyramidal. So that was square pyramidal. Well, here on this one, and what happened here, because of the non-bonded pair, remember a non-bonded pair takes up a little bit more space. And so it just made that bond angle a little less than 90 degrees. Well, here again, the non-bonding pair is going to go right here. And so what we have then is now all these are on the same plane. And if you can see this, it looks like a square. And so this is going to be called square planar. So the final shape. So it's square planar. And this one, the bond angles, because the non-bonding pairs are up here, they're up here, and they're down here, they kind of cancel out. So in this case, truly the bond angles, everything is 90 degrees. And something we're going to talk about here in a second, the example I gave here was XCF4. This is going to be nonpolar. If you look at this, and we're going to talk about the polarity thing here in a second, but if I look at this, everything is symmetrical here, meaning all the poles are going to cancel out. Okay, and that concludes the shape. So if you look, so again, if you look at this, I'm going to leave this up. I don't know if this will be up when you guys are here, because Mr. Berg will be back in here. I'm going to see if I can keep it up, I will, maybe one day. But this would be a good thing to take a picture of or have written down. It helps me out. It's a good analysis. And again, everything is based off the electron domains, and then again, a lot of shapes from first year chem, like linear, the trigonal planar, which is the flat triangle, bent, but now there's two bents, and so you got to distinguish the bond angle, tetrahedral and pyramidal, but then all of these down here were new shapes. And so definitely stuff that you guys are going to have to do problems with. Okay, now the last part of this chapter is going to be just kind of something that we've already went over now, which is the polarity stuff. So we're not going to take a lot of time on this in the notes, but let me go back to the notes. Okay, so this is going to be on polarity. It's going to be, I think, some that are familiar, some that we have had in the past. Okay, so this is right where we were. Okay, finishing up shapes. Okay, so, well, I guess before we get into polarity, I'm just going to leave this up here for a minute. I'm going to have you guys try these. So often, let me show you one here that we'll actually, I think we're going to do this in this Tinker Toy lab. We'll actually build this, but often there will be more than one central atom, and there will be more than one shape in the molecule. So here's an example, the shape of CH3OH. So this, in this case, there is more than one shape of this. Okay, and I'm going to show you that. But again, I'm going to do the dot structure. Okay, so let's do the, okay, so CH3OH. So if I do the dot structure, and this time both of these C and O are kind of the central atoms. They're both in the second row. They're not going to have an expanded octet. So it's going to look like this, and then CH3, and again, I'm hoping maybe, you know, and again, they were talking about, it sounds like what Dr. Page was saying, that there's a chance at a later point in time you guys will be back to a normal schedule, which would be wonderful. But you know, depending on what is going on, but after we're done with the AP test, we might spend a couple days on some basic basic organic chemistry. But if you see CH3 in organic chemistry, that's going to go together. That C is going to go with 3 H's, and then the OH is going to go together. So here's the dot structure. So if I clean this up a little bit, and this is what I was talking about, in that there's two central atoms here. So to identify the shape, So there's carbon and there's oxygen. But again, I did the dot structure, still doing the same. I'm still doing the same process. I'm doing the dot structure, and I am counting the electron domains. So if I look at around the carbon, there's 1, 2, 3, 4 electron domains, no non-bonded electrons. So again, if I come over here, again, I don't know what you can see and not see. That's this right here. There's 4 electron domains. There's tetrahedral. And so around the carbon, this organic molecule, so around the carbon here, this shape would be tetrahedral. And then the oxygen, so again, I count the electron domains. So 1, 2, and then 3, 4. So there's 4 electron domains, but there's 2 non-bonded electrons. And so around that, so this is still in the family of 4 electron domains, but it's got 2 non-bonded electrons. So this is bent. So around the oxygen, the shape, so around the oxygen, the shape is bent. This is bent at less than 109.5. Where this would be 109.5. Okay, so there's an example of shapes. Some of these organic molecules are like that. Okay, I want to just take 2 minutes here, and I want you guys to try some of these. Okay, so let me put them up here on the screen. And I mean, for right now, you're learning these, and hopefully in the book there's examples, in the reviews I've given you on the quizzes, there's going to be some of these in terms of determining the shape. Okay, so we just talked about the shape of CH3OH. Okay, so let's take a minute and let's try predict the shape of these. So let's just take a minute. I'll be quiet here. I'll give you guys a minute or two and try each of these. And again, I'm going to do the dots. I'm going to count the electron domains. So if you haven't been working on these, give us a minute to work on these. So go ahead and try and determine the shapes and the bond angles for each one of these. The shapes and the bond angles. So I'm just going to be quiet here for a minute.
Mr. Wood, while we're doing this, I just have a quick question about kind of something not related to this.
Yeah, go ahead.
Where are the videos of these recordings that you're doing? Because I was trying to review it over the weekend and I couldn't find them.
I've got them. I've just got them saved on my computer. So if you want them, or if you want a specific one, and this is true of any of you, just email me and I'll email you the link back.
Okay, perfect. Yeah, I would love them. I was trying to review them because this unit is kind of confusing for me. So I was just trying to review, and I couldn't find them.
Sometime, whatever you want, you just email me, and whatever, if there's a specific lesson, or if you just want all the ones that we've done in class. I'm talking about class. I haven't posted them just because I think it gets to be too much. But if you want them, and this for Allie or anybody, just email me, and I'll just email you whatever link you want or all the links.
Okay, thank you.
It definitely is some new stuff. It's some review, but it's definitely some new stuff. So we're doing the shape and the name, the shape, and the bond angle. Okay, I'm going to give you one more minute here. Okay, we ready to go over this? Still working on it? Let's still work on it then a little longer.
Yeah, just one more minute, please.
Okay. Okay, I'm going to go over these guys and again, so I'm going to do the same process that we did. So ASH3, so I'm going to do the dots. And so if I count the valence electrons, arsenic has 5, it's in nitrogen's column, and hydrogen is 1 times 3 is 3. So I get 8 dots. So I get arsenic and it's connected to the 3 hydrogens like that. And remember, hydrogen is one by far and away the exception that we use the most often. That doesn't have 8 electrons in its outer shell. It has 2, and so it's fine. So if I put arsenic here like this, there's the dot structure. So there's the dot structure. So I count the electron domains. There's 1, 2, 3, 4. So there's 4 electron domains. So if I got 4 electron domains, and I've got a non-bonded pair. The name of this shape is trigonal planar. I'm sorry, not trigonal planar, trigonal pyramidal. Trigonal pyramidal. And the bond angle here is a little less than 109.5. Okay, so the tetrahedral shape, the bond angle of tetrahedral is 109.5, but the non-bonded pair just shrinks it down a little bit. And the way that we would diagram that in 2 dimensions, and you again, one day when you guys come back, you'll build this, but we'll have arsenic in the middle, and one of the hydrogens will come towards you, and you'll see that. So again, if it comes towards me, I kind of shade it in, and then the other 2 hydrogens would be going away from me. So it would look like this. So again, if something's going away from me, I show a dashed line. If something's coming towards me, I show it coming out. So as best you can in 3 dimensions, that's the way that would look. Okay, anytime you guys got a question, ask me. But again, dots, electron domains, and then some memorization. Okay, then on to OF2. So if I do the valence electrons here, oxygen 6, fluorine 7, 7 times 2 is 14, so I get 20 total dots. Okay, so I'm going to put oxygen in the middle, and the fluorines around it, and I'll fill everything's octet. Slow down here, I don't want to go too fast. Okay, so then if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, everything is good. Okay, so I did the dots. I counted the electron domains, and the electron domains here are 4. Okay, so 1, 2, and then 3, 4. So 4 electron domains with 2 non-bonded electrons. This takes the shape of bent. The bond angle is less than 109.5. So just like the ASH3, this is a derivative. This is in the family of 4 electron domains, which is the tetrahedral shape. And so in this case, they would be in the same plane. So it would be like this. This is how we would diagram it. Okay, the next one. So aluminum has 3 valence electrons and chlorine has 7. 7 times 4 is 28. And then -1, so that means 1 more. It means there's gained 1 more electron. So I have 32 total dots. Okay, so
Mr. Wood, I have a quick question.
yes.
I'm confused of how you're finding that angle. Like, is it just the same for the shape?
Yeah, what this shape is based off, because it's 4 electron domains, the bond angle, the base bond angle, Juliana, is 109.5.
Okay.
So it's kind of like for me, and of course I've done it, and you guys are just learning it, but 2 electron domains is linear, 3, and its bond angle is 180. So really, the electron domains are connected to the bond angle. So 2 electron domains is 180, 3 electron domains is 120, 4 like the first 2 were 109.5. Okay, and then 5 electron domains would be 90 in the axial and 120 in the equatorial. Does that help? Does that make sense to me?
Yeah, that helps. Thank you.
It's a good question. Okay, so back here, so I get aluminum is the center. The chlorines are around it. Okay, so again, if I count the electron domains around the central atom, 1, 2, 3, 4. So to Juliana's point, that's a really good point. This is again 4 electron domains, so the base bond angle is 109.5. And in this case, since there's no non-bonded electrons, this is tetrahedral. So it's tetrahedral and it's 109.5. Okay, I'm going to do these 2 up here. So I3 negative. Okay, so I3 negative. So again, I'm going to count the valence electrons. Count the valence electrons. So iodine is 7 times 3 is 21, and then 1 more is 22. So I get 22 total dots with this. So all I have are iodine. So I have iodine connected to iodine, so it's like that. And then I fill the outer shells. So I fill the octets. So really, really doing a lot of dots now. So we're really here in kind of a little bit past midway January, dots and shapes, dots and shapes. And what we'll get into here a little bit later, in a few minutes, chapter 9, what chapter 9 is about is really explaining the dots. That's what it's about. But back to this. So I get 22 dots. So I have 2, 4, 6, 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, I get 22. So again, I'm going to add to the central atom. So it's like that. So now if I count the electron domains, I've got 1, 2. So a non-bonded pair is 1. So I've got 1, 2, 3, 4, 5. So this 5 electron domains. So the base, to Juliana's point, the base shape here is the trigonal planar. Now that's not what this is going to be. I'm sorry, the trigonal bipyramidal. I can say that right. The big old, this is the 5 electron domains, which is here and here, which is the axial, and then here's the equatorial. That's the base shape. But remember the non-bonding pairs. The non-bonding pairs here always go off the central atom, or sorry, they go off the central atom, but they go off the equatorial phase. So they're going to be non-bonded pair here, here, and here, which leaves this. So this is going to be linear. This shape is linear. This is different linear than the 2 electron domains, and the bond angle here is 180 degrees. And this is where this is new. And This is where, again, it's really good to be doing the problems in the book, doing the problems on the review. Okay, and then the final one was C2H4. So here's an organic molecule. Organic molecules usually have carbon and hydrogen in them, and a lot of times these are going to have, they're not going to come up very often for us, but these are going to have more than one central atom, like CH3OH. That's going to happen here. So I'm just going to go back and do dots the old way. These organic molecules. So I've got 2 carbons, and then I have 4 H's. So I'll put 2 over here, and I'll put 2 over here. So I did 2 carbons with 4 valence electrons, 4 hydrogens, so 2 here and 2 here. And then I just pair up the single dots. So slow down. So I paired up there, 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 there. And then again, I want to pair up the single dots, so I end up doing this. So if I clean this up a little bit, looks like that. So I really have 2 central atoms. I have here and here. Both of these are central atoms, both of these carbons. And so if I count the electron domains, a double bond is 1 electron domain. So 1, 2, 3. So 3 electron domains. The 3 electron domains looks like this. It looks like the flat triangle. So it's 120 degrees and is the base bond angle. And this is the shape, the base shape is the trigonal planar. It's really the triangle is what it is. And that's what we have here. We have 2 of those. We have trigonal planar on both of those. So around both the carbons, we have triangles. And if you looked at it, you actually, if you built it, you'd see a triangle here and you'd see a triangle. Okay, so definitely want to be, so the bond angle there was 120, and we just have 2 triangles, 2 trigonal planars just stuck together. Okay, now let's finish up this chapter. I've been on it now for a while. Okay, so now the final part of this chapter we've really kind of addressed already, like I said, which is the idea of polarity. So a dipole is a molecule with a charge separation causing a partial positive and a partial negative region in a molecule. Another term that you'll see once in a while in these problems is called a dipole moment. If you see that, it's just, they're just simply saying this molecule is polar. Dipole moment. So we're just saying the molecule has a positive and a negative. And then here's a good illustration of this. And again, I'll just let you guys, for those that are taking notes, for those that are awake and taking notes, which is some of you, which is probably a lot of you. But all dipole molecules will orient in one direction when placed between 2 oppositely charged plates. That's because they're charged. So all dipole molecules will orient in one direction when placed between 2 oppositely charged particles or plates. So if you look on in that diagram, the one on the left, A, the plates aren't charged. There's no positive or negative. And so the molecules, the HF, which is a very, very polar molecule, it doesn't align any specific way. But on the one on the right, where the plates now become charged, so in the diagram B, the plate on the left is negative, the plate on the right is positive. Well, now remember that opposites attract. So now the molecules take a specific, they align, is what that's saying. And that's because they're polar. Okay, and then to determine whether a molecule is polar, that has a dipole moment. So again, that's just a vocabulary thing to say it has a dipole moment. you look at the geometry of the molecule. And in the thing over here on the board, we talked about, is this shape going to lead to polar or nonpolar? The other factor, though, is the electronegativity of each atom. So again, I'll slow down here and let you guys copy this down. And what that means, the electronegativity of each atom. So again, like I tried to say many times, okay, and we'll come back to this in chapter 10 here probably next week. But if we have a metal and a nonmetal, it's ionic. Here we're talking about two nonmetals. If we have two nonmetals, and one of those nonmetals is that upper right-hand section of the nonmetal group, NOF or Cl. So if one of the nonmetals is that, then there's going to be a difference in electronegativity. Depending on the shape, it could be polar. But if it's two nonmetals not including NOF or Cl, then even though its shape could lead to polarity, because there's just no difference in electronegativity, it wouldn't be polar. So you got to look at the shape. Geometry again means shape, the shape of the molecule, as well as the elements involved in the bond. So determine the polarity and dipole moment of water. And this we've done many times. So again, what I would do is I'd figure out the geometry of the molecule, the shape, and then I'd ask myself, do these two elements have a difference in electronegativity if it's one of those shapes that's polar? And of course, water, it seems like we've done many times now. But water shape is bent, which that bent is always going to be polar if the elements involved have a difference in electronegativity. And that's what this illustration shows. And at the end of one chapter, maybe it's chapter 10, I kind of go over water. Water has all these unique properties. And so water is polar. Now, a good question you could ask is, let's just say, of course, it wouldn't work because carbon has different valence electrons, but instead of, let's just say that in place of the oxygen, we had carbon, and it was a bent shape, which again, of course, it couldn't be, but let's just say it was, just for the sake of example. So even though the shape, if we had carbon bonded to two hydrogens in a bent shape, so bond angle less than 109.5, the shape would lead you to say polar. But then I go back to number 2, the electronegativity of each atom. Well, because carbon and hydrogen's electronegativity is almost the same, then it's not going to be, the overall molecule would be nonpolar. And that's what I mean by, okay, number 1, the shape, okay, the geometry, and then number 2, the electronegativity of each element. Okay, and then here's NH3 and NH3. So again, if we go back, and look at what it says, determine the polarity and the dipole moment. So those, again, dipole moment is just, is it polar? And then if it is polar, which end is positive, which end is negative? And so because NH3, again, NH3 is ammonia. There's a couple molecules that come up a lot, not water, but NH3 is one of them. It's ammonia. And CH4 is another one. CH4 is methane. But that's not the point here. The point here is, so if I did the dots, there's 4 electron domains with one non-bonded pair. This would be the trigonal pyramidal, which is going to be polar. And so this molecule would be polar. And again, with this molecule we've done. Okay, here's another one that we've done, CO2. Now this goes back, if you do the dots, and you predict the shape, this has got 2 electron domains, which is going to be linear. So the polarity and the dipole moment of CO2. So because it's linear, even though it's got 2 oxygens, which is going to have a significant difference in electronegativity than carbon, but because that shape, that geometry leads to nonpolar, this molecule, even though polar bonds, it's overall nonpolar, because like a big tug of war where the poles cancel out. Okay, and then there's one more here. The polarity of CCl4 and CHCl3. This one I'm actually going to write on the board for you guys. So the tetrahedral shape is nonpolar if all the elements are the same on the perimeter. And this goes back to the electronegativity, and that's what this diagram is showing. So again, for those that are taking notes, I'll give you a second to copy this down. Okay, so let me just write these on the board, kind of try and diagram these so you guys can see these. Okay, so I have CCl4, and I have CHCl3. So if I did the dots in both of these cases, I have 4 plus 7 times 4 is 28, so I get 32 total dots. If I go back and just doing the dots. And then I've got 8, 16, 24, 32, so it's all good. So this has 4 electron domains, so this would be tetrahedral. So I'm just going to draw it like this. Technically, like it shows in the notes, it's better than this, better than the diagram's better than this. But this gets you the idea. This in the bond angle is 109.5. But in this bond, again, if you have NOF or Cl, that upper right-hand section, that's one of these. That's a polar bond, but that's a polar bond. But they're equal and opposite. They're equal poles, they cancel out. And the same thing happens here and here. So this molecule, even though it has polar bonds, every 4, it has 4 polar bonds, this is nonpolar. This is what I was saying, okay? The shape, the tetrahedral shape is nonpolar if you have the same elements out here. But if I go over here, so I've got, if I go back, I've got carbon is 4, hydrogen is 1, counting the valence electrons, so then 7 times 3 is 21. So let's see here, I've got 26 total dots. So carbon in the middle. I'll slow down here. But hydrogen, remember, is one of those that needs just 2 valence electrons to fill its outer shell. So I go here, like that. So this shape and this shape are the same. They're both tetrahedral. They're both 109.5. But the electronegativities are different because of this. So when you diagram this, it's like so. So again, in the way I've diagrammed it, in the horizontal, everything cancels out. But technically, that's a nonpolar bond. But there's a pull down, and there's nothing to cancel that. So this molecule, again, it's based off the shape and the electronegativity of the elements. Well, because this that bond there is really nonpolar, there's nothing to cancel out. This is a molecule that has a dipole moment that is polar. There's a negative and a positive in it. So when you are determining polarity, the shapes, and that's why I included that in that big table that I've got over here on the left side of the board. But then it also depends on the electronegativity of the elements. Okay, and there's another one here that I'm just going to go through kind of quickly. And this is another organic molecule. And at the upper left-hand diagram, everything would cancel out, so it'd be nonpolar, kind of the way they're oriented, the chlorines and the hydrogens. So the trans would be not nonpolar, but the cis, because the 2 chlorines are below and the hydrogens are above, it would be polar. And so all that being said, that is, again, what I've got on the board behind me is more important. But note the problems. So we are closing the book here on chapter 8. And again, it would be really good. Things you guys can be working on now is the quiz. You can be working on the problems from chapter 8. We're going to just get into chapter 9 a little bit. And again, I'll post a lesson for tomorrow that you guys can watch, get a little bit more into chapter 9. I always want to talk about this next slide. This is nothing I'm going to hold you to, but I think, again, and I actually start the next chapter with a couple of these little things, but how soap works. So water is polar. The molecules that compose grease and dirt are nonpolar. So molecules that compose soap have a structure where one end of the molecule is polar and one is nonpolar. So if you look on the diagram in the bottom right hand there with all those C's, and on one end it's got the red the red oxygens and Na, that end is polar. Well, the other end is nonpolar. So hydrocarbon chains are always nonpolar because the carbon and the hydrogen's electronegativity are almost the same. But the polar in my diagram, the right end is attracted to water and the nonpolar end is attracted to grease and dirt. So the way this works is you throw in your dirty clothes in the washing machine, and the molecule, the way it's written there on the bottom of the page, the right end of the molecule grabs a hold of water because it's polar, like dissolves like, but the left end of the molecule adds grease and dirt, which is nonpolar, and so you can remove the grease and dirt from your clothes or from your hands, how that works. So, okay, good. So we are done with chapter 8. Okay, so let's get into, and I know we don't have very much time left, but let's just at least start chapter 9 a little bit. And then I'll post not a long lesson, but a little bit of a lesson for tomorrow. And you guys can be working on stuff just again from chapter 8 and the quiz and so on. Okay, so into chapter 9. And chapter 9 is truly a continuation. And I probably in the video that I'll talk tomorrow, there's two main theories that go with really explaining how bonding works or explaining the dots. And the first one is the one I'm going to hold you to, and I think it's kind of makes sense. And I'm going to talk about it. I don't think I'll get to it today, but I'll talk about it tomorrow and Thursday. But that's why there's so few problems here, because we're only doing half of the chapter. The other half of the chapter is, if you guys go and take chemistry beyond our class, you guys would get into this second model, which again, I'm going to talk about just briefly. I'll talk about tomorrow in the YouTube video I'll post, and probably a little bit on Thursday. Okay, so there are the problems for chapter 9. Here's just another one of these for your information things. I'm the Diet Coke guy. Says chemistry and artificial sweeteners. Artificial sweeteners like aspartame, which is in diet sodas, NutraSweet, tastes sweet but has no calories. Why? Taste and caloric value are independent of each other. The calorie value of food depends on the energy released. And so there's a reaction. It's very exothermic. So there's the combustion of sugar, meaning the body metabolizes 5,644 kilojoules of energy. Some sweeteners are not metabolized at all. They pass through the body unchanged. Aspartame is metabolized, but a much lower caloric content. Taste, now get this, taste is independent of metabolism. Taste originates in the tongue, where specialized cells act as a highly sensitive and specific molecular detectors, receptive pockets. And so the main factor of sweetness of sugar is its shape and charge distribution. Okay, so some chemistry there. Artificial sweeteners taste sweet because how they fit into these receptor pockets like sugar. In fact, they bind more tightly than sugar, making them taste sweeter than sugar. Aspartame is 200 times sweeter than sugar. So even though they don't have the caloric content, because of how they fit into these receptive areas in our tongue, it makes it taste sweet. Immune response, sense of smell, and many types of drugs all depend on shape and charge distribution with specific interactions. Our ability to determine the shapes of key biological molecules is largely responsible for the revolution in biology over the last 50 years. And we're going to continue to study those shapes and polarity. Okay, this is a good place, I think, to stop. This is where we're going to pick up. We're going to pick up in the video that I'm going to put up tomorrow. Okay, so I'm going to stop there. Any questions?
No, Mr.
Okay. So everybody else, time to wake up. Time to wake up now. Get ready for your next class. So I'm done. If you guys don't have any questions, I will talk to you again. Posted lesson tomorrow. No Google Meet tomorrow. Google Meet again on Thursday. Quiz on 8 and 9 will be due when I see you in person. You'll actually hand it to me on Monday or Tuesday. Okay. If you guys don't have any questions, I'll see you. See you, Mason.
Thank you.
Thank you.
Well, thank you.
See you guys. See you guys. Have a good day.
Thank you for the lesson, Mr. Wood.
Tyler, have a good day, buddy.
Thank you.
Hey, I just had, I didn't know if you saw my email that I sent you about a couple questions I had on the lab.
I haven't opened it up yet, Allie.
All good. I was just
What are
basically
the questions?
asking, I was confused on, 7, 8, and 9. I mean, like, I understand what they're saying. I was just kind of confused on how to find it.
You have a minute right now?
Um,
You have class?
I do have class 3rd period.
Okay. Do you want to just do a Google Meet later today, or you want to try and do it?
I have 7th off. Is it okay if we meet during 7th?
Hey, can you email me maybe, I don't know, email me like right after 6th, and then I'll get on and we'll do it. I don't think it'll take that long. And then you can get it all right and send me your lab, and I won't count it late.
Beautiful. Thank you. I appreciate it.
I'll talk to you later today.
Okay, bye.